So today we're going to start a new chapter uh, called as complex numbers. It's one more new number system which you're going to learn. Okay, a far bigger set. So just before we start off with complex numbers, just to recall what are the number system we know and probably how they came into existence. Right. So the most basic number system is the natural numbers, usually denoted with a capital letter N. Right. They are nothing but our counting numbers, 1, 2, 3, so on. Okay. So after that, we thought of say whole numbers, which include zero. Okay. And then came probably the integers or the negative numbers here, minus one, minus two, minus three, so on. So we can all think of why we added zero later or got into negative numbers, right? So we can think of examples. Probably we add say 2 and minus 2, which gives 0. It makes sense. Okay. In the real world examples, probably suppose I give you 10 bucks, we can write it as minus 10 for you and plus 10 for me. Right. So it makes sense, right? We need those numbers just to write our daily calculations as well. Okay. So probably you can write debt as negative or something like that. Okay. I'm just trying to figure out the progression of why we need numbers. After this, probably we got into fractions, right? What we call as rational numbers. Let me just combine this set and write it as integers. Then after let me draw the number line. This is 0, this is 1, this is 2, so on. Okay. So till now we left the gap what was there in between, this gap, right? We didn't really focus on this gap. We just looked at the numbers which are right, very easy to calculate, very easy to add and multiply and so on. Okay. So going ahead, so we came across rational numbers. Now we define rational numbers as any number in the form of p by q, where q is not equal to 0. The specific condition why we can't have q equal to 0. So now when we gave this definition, we see that we could take many things in between. Okay. Now you may think, why would we require such a kind of definition of rational numbers? Right? Even before rational numbers, you can think it as fractions, right? Obviously, we want to know what is half, right? If I want to eat half of the pizza, I should be able to convey that, right? Or 1/4 or one slice. One slice might be 1/8, right? So basically, we started dividing the numbers into smaller parts, okay, which is nothing but say your fractions. So to get it well defined, we wrote it as p by q, right? And the only condition is q not being 0, okay? But we forget to mention that p and q must be integers. Yeah. We assume that it's true. Oh, sorry, the integers, the symbol for integers or the letter for integers is capital Z. Now you can see 2 by 3, all these fractions, what we talked about, come under rational numbers. Then there's another category called as irrational numbers. Again, what we came across is, even after taking rational numbers, there were a lot of numbers that were remaining in this gap. Okay, we could only pick particular numbers. There is something in between, something between 1 by 2 and 1 by 3, right? You could decrease the fraction, but still you would get numbers in between. Okay. Then while calculating probably the diagonal of a square, somewhere near the circumference of the circle, right, we realize that there are numbers other than rational numbers. Okay. So we come into irrational numbers. So the easiest definition what we give for irrational numbers are any number that's not rational is irrational. Okay. So we say that root 2, root 3, so on. There's some other special numbers like pi or the Euler's number, etc. They also come under the rational numbers. Now, looking at this number line, you can see we have filled this gap, right, completely. Now we don't have any gap. So we started off with numbers. Now we have infinitely many points, right, all with rational and irrational numbers. Even these integers, right, what we call them rational numbers itself because we can write it in terms of fraction. Okay, so we can write in terms of fractions, so they are rational numbers. So we come across this biggest set, which is called as real numbers. The combination of these two, the rational and irrational, became real numbers. So in a day-to-day life, whatever calculations we require are all done using real numbers. Okay. So just think about it. This is the biggest set we can think of, right? Then we are trying to define something new here, something called as complex numbers. How do complex numbers fit in? Or where do we find more numbers from? Okay. Because looking at a number line, at least we are taken care of each and every point we feel. Okay. This is more to do with our calculations, like when we try to calculate polynomials, or probably when you have heard about quadratic equations, right? You say that roots are real and roots are imaginary, right? So, what do you mean by imaginary? Okay. There is some relation between complex numbers and the imaginary roots there, okay? Just to give you an idea. So, let me get into the definition of complex number. What is a complex number? And how did we start with complex numbers? So you can think of something like this: x square, we know it's a positive number, right? We always know it's a positive number. But what if x square is equal to minus 1? So if I put in a number for x square and I get negative 1, okay, in a real numbers, it's not positive. So this opens a lot of possibilities now where we start off with complex numbers. This is a very important number because we have all the calculations related to this x equal to root of minus 1. Because any negative root, okay, sorry, not negative root, sorry, root of a negative number can always be written in terms of this root of minus 1. We'll see how to write that. Therefore, we name this as I. That is, I is root of minus 1. So going ahead, wherever I write I, that means it's root of minus 1. Now just look at it. If I want to write root of minus 9, I can always write this as root 9 into root of minus 1. So whenever there's a negative number, it's taken care of. Okay. So this will be nothing but root 9 is 3 into I. Even if it's root of minus pi, you can always write as root pi into root minus 1, which is nothing but root pi I. So coming back to the definition of a complex number is a number which can be written in the form of a plus ib. Now we know what is I. So a plus ib. Now let me define a and b also. A, b is nothing but belongs to, say, real numbers. So a and b are not complex. Okay. A and b belongs to a set of real numbers. So just to give you an example, say 2 plus 3i. Okay. It need not be only positive, so you can have anything like 2 minus 10i. Right? We need not have only integers or rational numbers. We can have, say, 2.2 minus pi I. Everything is a complex number. So can you see what we have done? We have taken a set of real numbers, added an imaginary part, right? Added root of minus 1 and multiplied that with a real number. Now I'm taking care of two parts. One is the real part and one is the imaginary part. Okay. We'll come to the details later. Now just to note this down. So we either write it as in the form a plus ib or x plus iy. Okay, it's up to you. So let me just write it down. Complex numbers are usually denoted with a small letter z. Okay, and the entire set of complex numbers is usually denoted with the capital letters. So z is nothing but, say, x plus iy or a plus ib, where x and y belongs to real numbers. Now look at this x. X is only a real number, correct? And look at this y. Y has I multiplied to it. Okay. We know that I is nothing but root of minus 1. Okay. Therefore, we call x as the real part and y as the imaginary part. Just because it's we're writing down in that form. Okay. Imaginary part. So you may think, how should I represent root of minus 9? There's no real part to it. You can have the real part to be 0. So it can be 0 plus, say, root of minus 9. This is a number. This is a complex number. So this is nothing but what? We have already come across. This is 3i. Now, if I write 3i, that means what? The real part is 0. It's still a complex number with the real part being 0. Okay. So let me just give you some standard notation. So real part sometimes is written something like this. So if I say RE of Z, that means write the real part of the complex numbers. In this case, the original complex number was X. So this would be X. And for imaginary part, we usually use IM. So that denotes the imaginary part. So this one. Now you can see we've divided this number system. Just take it as a definition, right? So to be written in the form of x plus iy, where we have two parts. One is the real part, one is the imaginary part. We think how to represent a real number here. We can represent. Now, if any real number I want to write, like pi. So pi can be written as pi plus 0 into I. 0 times 0. Okay, there's no confusion there. 0 into root of minus 1 is 0. So in this case, what happens? Can you see that this is purely a real number? This is nothing but pi. Okay. Now you can clearly see that real number is nothing but a subset of complex numbers. Because there's a real part. If the imaginary part is 0, the entire part what we get is the entire number system of real numbers. Right? So there's the real numbers plus the imaginary part. Okay. So real numbers is actually a subset of complex numbers. Okay. Now to understand how to think about complex numbers. What do you mean when I write 2 plus 3i and say 4 plus 3i? Okay. Do they have any value? Like, is 2 plus 3i greater or 4 plus 3i greater? We really cannot compare this two. Okay. These are not exactly the numbers we deal with on a day-to-day basis, right? So, what we can never say that this is greater or this is greater. We have another notation to try to find the value of the complex number, or in better words, magnitude of a complex number. For example, if I name this as Z1, okay, I can find the magnitude of Z1 by just finding the square root of, say, 2 square plus 3 square. Okay, we'll come to that, what it is. And here, this other number is, say, Z2, the magnitude of this is nothing but root of 4 square plus 3 square. We can simplify that. This is 4 plus 9, this is root 13. And this is root 4 square plus 3 square is the standard. We know that it's 5 square. So it's 5. Now, just because the magnitude of Z2 is greater doesn't mean that the complex number is greater or something. We can never compare these. Okay. So let's not compare Z1, Z, but we can compare the magnitude. Okay. So coming to the important property, first important property is the magnitude, okay, or modulus. Is nothing but, suppose the complex number is nothing but x plus iy. So let me write x plus iy. Yeah. Right. So the magnitude will be root of x square plus y square. Now if it's negative, again we can write minus x whole square. So it will be still x square. So it doesn't really matter. So this is nothing but one of the important properties of a complex number. We talk in terms of magnitude or modulus. There's one more important part which will come later when we talk about the graphs of a complex number. This just to complete the argument here. So we can't compare the two complex numbers, but you can always equate it. Let me show you. If I say that a plus say 2i is equal to say 3 plus bi. If I say that two complex numbers are equal, they can be only equal if these two are equal. and these two are equal. That means if two complex numbers z1 and z2 are equal, that means the real part of z1 must be equal to real part of z2, right? And the imaginary part of z1 should be equal to imaginary part of z2. So if both are equal, then we say the complex number is equal. So basically what I'm saying is, if 3 plus 4i is the complex number, it can't be equal to some other number. It should be equal to 3 plus 4i itself, right? If they are variables, right, we can easily compare. For example, in this problem, you can guess what is A. A is nothing but equal to 3 because it should be equal to the real part. And similarly, you can guess what B is. B is nothing but 2. So therefore, complex numbers, if they're equal, right, the real parts are equal and the imaginary parts are equal. We never compare them to be greater or lesser. Now we'll try to plot these complex numbers into a special plane called as the Argand plane. Right? You'll be surprised by what I draw because it looks like nothing but your complex. Sorry, it looks like your coordinate system itself. Only difference is in a coordinate system we don't have a real and imaginary part, right? So what we do is we take the real part here, it's also known as the real axis. Okay, and this y, usually what is denoted y, would be an imaginary axis. Fine. So you can guess this would be origin. Okay. Now here you have a real axis, so the numbers are 1, 2, 3, so on, including the rational numbers in between and the irrational numbers. On the other side, I would have -1, -2, -3, so on. Now, what would be on your imaginary axis? So these are nothing but you can write it as I, 2i, 3, and so on, or you can simply write it as 1, 2, 3, because we know that it's the imaginary axis. I'll consider this as somewhat relating to I itself. So I need not really write I. I can simply write 1, 2, 3. We'll see an example which will be much more clear. We extend this. This will be -3, -2. So let us take an example. Say that is say 3 plus 4i. Can you think of how to plot this point on the graph? So it is nothing but 3. 3 is the real part. So you can see this is the part here. Okay. 3 is the real part. And we need 4 in the imaginary part. 4 is somewhere here above. So let me just try to draw it again. So 4 will be somewhere here. So if I have to draw this, you can see 3 goes here. 4 goes here. These are not lines that I'm drawing. Okay. I'm just trying to show you the point. Like our coordinate system, instead of having numbers in x and y, both sides, what we are doing is we are having x as a real part and y as your imaginary part. Now this point is nothing but say 3, 4, or to write in terms of the complex numbers, it's 3 plus 4i. So you're talking about this point itself. So it's similar, somewhat similar, right? But you can see that I can represent a complex number here. Okay. So now just think, what do you mean by modulus? We know the modulus of this complex number is nothing but root of say 3 square plus 4 square, which is nothing but 5. Right? You know it's 5. So graphically, can you think of what can be 5? But what do you mean by root of that? 3 square plus 4 square. Okay, if you guessed, it's very nice. So I hope you could guess. It's nothing but the diagonal here. Look at this. Or the distance from the origin. Because this is nothing but 4, this is nothing but 3. We know the hypotenuse is nothing but 3 square plus 4 square. Right? So this would be nothing but root of 3 square plus 4 square. So any point I plot on this graph, which is also known as the Argand plane, right? So the modulus would be the distance from the origin, right? So modulus of z, nothing but root of x square plus y square. You can see by distance formula also, something but the coordinate of x and coordinate of y connecting to the origin, right? So I told you there are two important aspects of a complex number which you need to know. One is the modulus or the magnitude. The second is this angle. If you have learned more about coordinate geometry, you would have come across polar coordinates as well, right? There also you could see something relating to the radius and the angle, so on. This is somewhat similar to that. So what is that angle? I think in this case, you can figure out if you take this as theta, so tan theta, we know that is nothing but 4 by 3. Because opposite by, adjacent, right? So it's 4 divided by 3. So theta is nothing but tan inverse of 4. So this angle, what we got right now, the tan inverse of 4 by 3, is nothing but your argument of your complex. So argument, you can think of in general what will happen. Suppose the point is x plus iy. Okay. X plus iy. You can see that this will be hypotenuse. The height is nothing but your y-axis, and this is your base. So x. So this, if this is theta, the argument is nothing but theta, which is tan inverse of y by x. Okay. Tan inverse is nothing but an inverse function. Basically, if you say tan theta is equal to 1, you should be able to guess what theta is. Theta is nothing but 45 degrees. Right? There are more solutions to it, but in this case, what we're talking about tan inverse is a limited range. So we always talk about an angle between minus pi by 2 and pi by 2, right? So just to guess that angle, we are writing in terms of tan inverse. So tan inverse of y by x. So this is an important point for the concept. So using the magnitude and argument, right? So you can fix the complex number. That's why it's very important. So we need both the modulus and the angle. So for any complex number given, you can directly find the argument and the modulus. So for this x plus iy, we know what is the modulus, usually denoted with this symbol, right? Is nothing but root of x square plus y square. And the argument, we can write argument of something like this, okay, is equal to tan inverse of y by x. Tan inverse of y by x. Any complex number given, we should be able to find these two. So let's look at other properties, right? Like something like addition, subtraction. Can we do that to complex numbers? Because we already established that I can't check whether it's greater or less. I can't compare it to complex numbers like I can do in real numbers, right? So let me write down 3 plus say I and 4 plus 5. Can I add these complex numbers? Okay. Again, let me name them as Z1 and Z2. Yes, I can do that. I can add or subtract, not an issue. So you take Z1 plus Z2. This is nothing but, let me write it down, 3 plus I plus 4 plus 5. Now the thing is how to add them. I told we can add them. So shall I combine everything and write as one number? No. Because I told you, a complex number is always represented in the form A plus IB. Right? So I should be able to write this also in the term A plus IB. So combine the real part, the simplest way to think about. So this is nothing but 7. Combine the imaginary part, I plus 5i, which is nothing but 6i. The sum of these two complex numbers is nothing but 7 plus 6i. Now you can guess for subtraction what can be done. You can follow the similar way. So it is nothing but 3 plus I minus 4 plus 5i. Or 3 minus 4 is minus 1. I minus 5, which is minus 4. So addition, we add the real parts together and the imaginary part together. Subtraction similarly. So subtraction nothing but minus into the addition part. That's all. Right? So you're basically adding with the minus sign. So again, it is the same. Real parts combined and imaginary part combined. But what should we do if I have to multiply, say Z1 into Z2? To multiply these two, can we figure out what is this multiplication? What is this number equal to? You can try this. So if you try it, So you simply have to multiply them, right? You can try to figure out what you get. 3 into 4 is nothing but 12 because it's a number. I'll simply write it down. 3 into 5i is 15i. Agreed. Now you have completed 3, so I into 4 is 4i. Now I into 5i is nothing but 5i square. I think till now you didn't have any problem because you had I and a real number. You could combine them somehow. But there's I square. Now, by definition, we know I is nothing but root minus 1, which is nothing but your imaginary number or imaginary unit, where we started off with complex numbers. So, I square is nothing but minus 1. So, I can simply substitute here it as minus 1. I'm going to get 12 plus 15i plus 4i minus 5, because I square is minus 1, I just multiplied. Now combine the real part. Real part is nothing but 7. Imaginary part is 19. So we were able to multiply these two complex numbers. Not so difficult. So it's multiplication is similar to what we do in algebra, right? For real numbers, right? X plus y into a plus b, right? We just multiply them individually. Only difference is we come across some complex numbers or imaginary numbers where we have to take care of the powers. Now, because you have done addition, subtraction, and multiplication, we have to look at division and what can be done there, right? Before trying division, right? There's one more concept in complex numbers, which is not really there in imaginary numbers. There is a sort of a similar technique when you have learned in probably quadratic equation. You have seen they come in pairs, but let us look at it. What exactly it happens, right? So a plus ib. If you look at this number, this is a complex number, right? But to find the conjugate of this number, I write as z1 bar. Okay. So what exactly is conjugate of a number? Same number, I write a minus ib. This is nothing but the conjugate. Now you may ask if minus a plus ib, even this is a conjugate. No. So what I'm doing is the sign of I, if it's positive, I'm making the sign of I negative. Okay. I'm changing the sign of I. So obviously, if it's negative, it becomes positive. Not the real part. Not the real part. Okay. There's no specific reason we took this as a convention, right? This is the definition for a conjugate. So what I do is a plus ib, I write a minus I, the conjugate of a plus ib. Suppose it is I plus 4, don't simply blindly write I minus 4 is the conjugate. No, it would be minus I plus 4, right? So we always change the sign of I itself. Now we know what is a conjugate. So can we just see some definitions here or some more properties using using the complex number and the conjugate, because we know how to add now. Can you see if I add these to what I'm going to get? I'm going to get 2a. What is a? Is nothing but the real part. So I'm going to get the real part twice the real part of. So I can define the real part of complex number something like this. Z plus, sorry, I've written Z1 everywhere. So let me write Z1. Z1 plus Z1 bar by 2. In general, if you want to ignore the Z, you can simply write something like this. In general, any complex number. Right? You have to be specific to this Z1. That's all. Then what would be the imaginary part? Yes, you have guessed. Just subtract them. So Z1 minus Z1 bar. If you just subtract them, you can see that A and A will get cancelled now. So divided by 2 I'll do. So this is nothing but IB or 2IB by 2. Okay. So it will be I into B. Just to ignore that I part, what I'll do is I'll divide by 2I. So I just need B, right? The imaginary part of it, not including I. So I can divide by 2I. So you can see what will happen now. A plus IB minus A minus IB by 2I, which is nothing but say 2IB by 2I. So this will get cancelled. B is nothing but your imaginary. So we can write in real part in terms of z and its conjugate, z plus z bar by 2, or z imaginary part is z minus z bar by 2. Okay. We'll come to more properties of conjugate. Before that, you have to go back to our problem and try to divide these numbers. Let's try dividing z1 by z2. This is the reason why I introduced conjugate in between. Can you figure out what is z1 by z2? So basically, I'm trying to divide 3 plus I by 4 plus 5. Now, the concept of conjugate we're going to apply here, because we don't know really how to divide the real part separately and imaginary part separately. What we're going to do is just multiply with the conjugate, because if I multiply with the conjugate, what happens? You're going to get a real number. Let's look at it. 3 plus I and 4 minus 5. Let's calculate the denominator first. So it is 4 into 4, which is 16. 4 into minus 5, 20i. 5 into 4 is plus 20i. 5 into 5. Minus 5 into I square. Okay. So minus 5 square into I square. Okay. Numerator, okay, we can simply do the multiplication. We've already done it. No, we have done for plus side, sorry. So it's 12 plus 4i. What else? Minus 59 minus 5i square. Fine. Look at the denominator. So this and this will be cancelled. What remains is 5 square, which is 25, with into minus 1. Okay. So this will be 16 plus 20. Numerator is nothing. Combine the parts. Now this is again minus 1. So minus 1 into minus 5, which is 5. 5 plus 12, 17. Minus 11i. Denominator, can you see it's a number right now? So again, it is in the form a plus ib. If you just divide it properly, you can write this as 17 divided by 25 plus 16 is 41 minus 11 by 40. Can you see we still have an imaginary part and real part? So what did we learn here? One thing, you can take it as property here itself, z1 into z1 bar. What do you get? Let us try a plus ib into a minus ib. Basically, I'm multiplying the complex number with its conjugate. I'm going to get a square plus aib minus aib minus I square b square. These two will get cancelled. I square is nothing but minus 1. So you're always going to get a square plus b square. You probably knew this because we know that a minus b into a plus b is a square minus b square, right? You could have used the formula, but just because it's complex numbers, let's try to multiply from the basics and try to get our results. So this is nothing but our magnitude square, right? So now you can see what we did when we had division. We simply wrote the conjugate here or multiplied with the conjugate, the numerator and denominator, just so that this denominator becomes a real. Now, when this is a real number, I can separately divide the two parts, the real part and the imaginary part. Okay. So any division, basically what we're going to do is we're going to multiply the conjugate. That way, it's different from our usual algebra. Okay. So let us try this problem. We want to write in terms of a plus ib, right? So numerator, we can just multiply. So it's 3 into 2 is 6. Now, again, 3 into minus root 5. So minus root 5i. Next term, 2 root 5i. And last term would be minus root 5 square into I square. Now, we know that denominator, to get rid of the denominator, all we can do is multiply with the conjugate. Well, multiply with the conjugate. Be careful, I is written first. So we'll write root 5 minus 2i. And numerator also will be root 5 minus 2. Let's simplify. Let's simplify. Numerator is 6. This will be 5 because of the minus sign. It will be 11 minus root 5. This into root 5 minus 12. Denominator, because it's conjugate, you already know it's nothing but 5 plus 4. 2 square. Root 5 square is 5. Now, again, multiplication in the numerator denominator is 9. So 11 root 5 minus 22i. Imaginary part minus 5i and plus 2 root 5. Now, both contains a rational and irrational part. We can separate them. But first, what we do is separate the real part and the imaginary part. Real part is this. Sorry, this is I square here. So real part would be this. So 11 minus 2, 9 root 5, right? And this would be 11 minus 2 is 9 root 5. And the remaining part would be minus 27i. Now, if you can divide by 9, so you will get root 5 minus, say, this is 3. So the final simplest form you can see is A is nothing but, if you want, A is root 5 and B is minus 3. If C is this, what is the magnitude of C? So we know that magnitude is nothing but root of x square plus y square, right? So it is nothing but root of, say, 12 square plus 5 square. So 12 square is 144. If you already know the Pythagoras triplet, you'll directly write it as 13. But still, let's continue. 144 plus 25, root of 169. This one. Fine. Next. If D is this, what is the argument of D? Now we know that argument is nothing but tan inverse of y by x. Okay. So what is y in this case? Remember to include the sign minus 2 and okay, minus 2 and so it's tan inverse of minus 1. Now I hope you people know this is nothing but tan inverse of negative number. Okay. So if you have some confusion, right, do one thing. If you're not particularly sure, you just see where the point lies. Okay, just think. So real part is positive, so it should be here. Imaginary part is negative, minus 2 is here. So the point is to be something like this. So can you see the angle? Angle will be this, right? It's nothing but minus pi by 4. Okay. So obviously, you can write in terms of this angle if you like. Okay. So it will be 2 pi minus pi by 4 that way. But this is easy to calculate in the negative direction, minus pi by 4. Okay. So if it was positive, you would have got pi by 4 like this by y by x. So therefore, you have to be careful. When the obtuse angle will see, right? So again, it is negative here, right? So based on which quadrant your point lies, it's easier to judge. That's why I wrote the point. So your point is here, right? So you can see it is nothing but minus pi by 4. If you write it as minus, say, 3 pi by 4, the 3 pi by 4 will lie somewhere here, okay, which is certainly not possible. The two conditions are, one is tan is anyhow positive in that quadrant. And the second thing is this angle should be acute, which we got is acute. So it should be lie in this coordinates. Okay, now A and B are points in the complex plane, which is a solution to this quadratic equation. So we don't really have to find A and B. They have asked multiple things after that. We can try to figure out that. But let's find out what A and B are anyways. So x square minus 2x plus 2 is the quadratic equation. So the root, so we can use the formula. So 2 plus or minus root of, this is 4 minus 4 into 2, which is 8 by 2. So this is nothing but 2 plus or minus root of minus 4 by 2. You can simplify this. We can divide by 2. This will be 1 plus or minus 2y. Sorry, this 2 will get cancelled. So 1. So the root of 4 will be 2, which will get cancelled. So 1 plus or minus 9. Now what is asked? We can simply quickly finish it off. Real part of the product A times B. Okay. So what is A? Let us assume one of the roots is A. Okay. Let us assume 1 plus I is A. So B would be 1 minus I. Is it okay? So what is the real part of the product A plus B into A minus? So A into B is 1 plus I into 1 minus I. This is only real part, there is no imaginary part at all because we know the modulus is 1 plus 1. So this is equal to 2. What is the imaginary part of the product A times B? This is 0. We already found out the product. This product is nothing but 2 plus 0I. Imaginary part is 0. What is the real part of the sum A plus B? Okay. A plus B, if you do, you are going to again get 2 because the I will get cancelled. So again, the real part of A plus B is 2. Imaginary part is 0 again. Because this is only a real number. So imaginary part is 0. What is the sum of the arguments? Remember, sum of the arguments in degrees of both A and B. Okay. So sum of the argument. Let us write the argument of A. Argument of A is tan inverse of y by x. So it's tan inverse of 1 by 1. So it is tan inverse of 1, which is 45 degrees. You know, pi by 4. Next case, tan inverse of minus 1 by 1. So we have already seen this. So it's nothing but tan inverse of minus 1. We will see the negative direction, right? Minus pi. The sum is pi by 4 plus minus of pi by 4, which is 0. Last one. What is the product of the magnitude of the modulus? Let us write the magnitude of A. It's root of 1 square plus 1 square. Magnitude of B, root of 1 square plus 1 square. This is root 2. This is root 2. We need the product of these two. You could have done this with formulas as well because we know that modulus of A into modulus of B is nothing but root 2 whole square, which is 2. Right? So this is nothing but the modulus of the number here, which we already knew was 2. Because we already multiply A and B, then we can take the modulus after that also, which we already knew it was 2. But because it was given in that form, we could have tried and just compared the numbers. That's all. The value of I per 1000. Okay. It looks pretty big, but let's see what I is. I is nothing but root of minus 1. Agree? So what is I square? I square is minus 1, the definition of complex number. Now it becomes a bit tricky. So I cube is nothing but I square into I. Agreed? But I square is minus 1. So I'm getting root of minus 1. I is root of 1. Then minus 1 minus I. So what would be I power 4? I power 4 is nothing but I square into I square. I square is minus 1. This is also minus 1. It's 1. Can you see what will I power 5 be? I power 5 is nothing but I power 4 into I. I power 4 is 1. That is a very important factor. If I power 4 is 1, then this will be equal to 1 I itself. Now again, I power 6, I can use the same logic. It's I power 4 into I square. And because I square is minus 1. Similarly, we can continue this pattern. So can you see that it repeats in a cycle of 4, right? This will be minus I. So what do we need? So I power n. I power n. If n is a multiple of 4, that is this case, n is a multiple of 4, then I power n will be equal to 1. If when I divide by 4, the remainder is 1, or the number is in the form 4k plus 1, which is the case? This case. So the number what I get is I itself. Suppose the number is in the form 4k plus 2, or the remainder is 2 when I divide by 4. It is I square or minus 1. It's 4k plus 3. That is minus I. Yeah, divided into basically when you divide by 4, what is the remainder? You get your answer. So now 1000 is the question. When you divide 1000 by 4, certainly the remainder is 0, not equal to. Remainder is 0. Remainder is 0, or it's in the form of 4k. So this is equal to 1. So any power given, it's very easy. Just divide by 4. See what is the remainder. Based on that, you get your answer. So what is the smallest in power positive integer of n for which this is true? Now see, we're comparing two complex numbers again, right? So if it is a plus ib and say c plus id, I'll equate a to c and b to d. But look at this problem. We can't directly equate because here there is a quotient, right? And here is just a plus ib form. Okay. Let's get these two into comparable form so we can do something about it. Okay. So what we can do, we can multiply with the conjugate inside. What we usually do whenever we have division. So we can multiply with 1 plus I. This is 1 plus I. Whole power n minus 1 is equal to minus 1. Inside, what will happen? Denominator is 1 plus 1 plus a square plus b square. Numerator, a plus b whole square. 1. This is plus I square, which is minus 1. Plus 2. Agree? Now look at it. How it simplifies. So numerator becomes 2i, denominator becomes 2. So 2 and 2 will be cancelled, which is nothing but I. So I power n minus 1 should be equal to minus I. Simple equation. I power n minus 1 is equal to minus I. Now, smallest positive number of n is given. What is the value when we get minus I? It's I cube. This is the first value which we get. It's I cube. So n minus 1 should be equal to 3, or n should be equal to 4. Right? What is the smallest positive integer value of k for which this is true? So 1 by I whole power k should be equal to 1. That means 1 by I power k is equal to 1. Cross multiply. I power k is equal to 1. When is I power k equal to 1? The first positive number we can think of is 4, where it's 1. Therefore, k is equal to 4.